Welcome everyone to the Critical Design Review presentation of the Bird Initiated Rubbish Disposal System, also known as the BIRDS project. Our wonderful team consists of Aidan Nipper, a photonics and science engineer, Will DeSalvo, photonics and science engineer, me, Rodrigo Guerra, electrical engineering, and Donovan Reynolds, computer engineer. And together we're here to bring the birds to life. We decided to take on this project because of the unfortunate reality that despite our best efforts to keep the planet clean, sometimes it feels like an unreachable dream. Due to our inability to leave a space clean, governments and communities are forced to actively invest in cleanup, whether it be from volunteer groups, convict labor, or outright salaried cleaners. It's a painful allocation of resources. In the absence of common sense solutions like preventing the generation of new waste and educating the public on proper waste disposal, we must consider the absurd. We chose birds because of three unique properties. First, they are omnipresent, which they are basically everywhere. They are intelligent enough to be trained so they can form correlations between their actions and something else. And they're cheap to bribe. You only need seeds and simple food. It's not too expensive. We have set three core goals for a successful implementation of a bird conditioner. The first is that the response time from when a bird deposits an item to when the system delivers a verdict must be short enough for the participating birds to make an association of their actions and the reward. Secondly, the system must deliver consistent decisions to reinforce the desired behavior. Otherwise, we risk losing our progress in the conditioning, or even worse, reinforcing unforeseen behaviors. And thirdly, the housing must operate autonomously for at least a week with no human intervention, and that means having enough storage for the food and the trash, and weatherproofing the critical components such as circuitry and boards.
These tables outline the engineering specifications for both the electrical and optical components of the birds, with the key specifications highlighted in yellow. Starting with electrical, the power draw from our PCB must be low, as the system will need to function on its own for a week at a time. The most important part of our system, the image processor, must deliver a recognition verdict within 2 seconds of an image being taken. Moving on to the optical components, a key specification for our camera systems will be the FOV or field of view of each camera, which is affected by the collimating lens or outermost lens. The focal lengths of the lens system are also important, as they will need to fit the object distances for the bird landing pad, 10 to 20 centimeters, and the bottom of the trash analysis chamber, 15 centimeters. Next, we have the engineering requirements for the birds. The key requirements here are the accuracies of each image recognition software, with the bird image processing requiring a 90% or higher accuracy, and the trash image processing requiring an 85% or higher accuracy. Below that are other key requirements for time durations, including the time it takes for food to be dispensed once trash has been recognized, which will need to be 2 seconds or less for the quickest positive feedback to happen.
The hardware block diagram shown here gives a breakdown of our main parts within the birds. A few noteworthy devices are the bird and trash imaging systems to the left with their optical designs shown, as well as the many peripheral components that will ensure every function offered by the birds will be executed. This diagram reveals the complexity of our system and the need for all of the components to work together in tandem.
Going into more detail on the functions of the PCB, we have three general categories. We have motion detectors, actuators, and communication. The first detector will be a capacitive sensor that will read changes in capacitance on a conductive plate. This will tell us whether there is something in the landing platform to take a picture of. The next detector is a laser and photodiode laser brake system that will detect whether an object has crossed through the laser path, and we can read that as a voltage drop across the photodiode. Then next we're going to the actuators. We will have a stepper motor rotating a screw conveyor a certain amount to deliver a specified amount of food for the birds. Then we have two servo motors that will operate the doors that allow access to the analysis chamber. And finally we have a trash sorter that is another servo motor that rotates a plate inside the analysis chamber, one side to discard and the other side to store into the trash storage. And then finally, we have the communication pins. We have 2 pins for bird camera and 2 pins for trash. One pin tells the Jetson to activate the bird camera, another one reads if the Jetson decides if it's a bird or not. Same with the trash. This is our housing design, and it can be divided into 4 general sections. Starting at the top, we have food storage and food dispensing. We will have a screw conveyor that rotates and delivers food into a predetermined location. Going underneath the food storage, we have the bird terminal, and we have doors that allow access to the analysis chamber. We're planning on having a capacitive plate sensor out here extending from the housing, but we're working on the structural support and how we're going to do that. We're going to have 2 cameras on the inner walls of the terminal, one looking down into the analysis chamber and the other one looking outside of the housing into the capacitive plate. Under the terminal, we have the laser plane sensor that will detect whether an object has crossed it to activate the trash camera. Under the laser plane, we have the analysis chamber that will have a plate inside of the cylinder that rotates either outside to discard it outside of the housing, or we can rotate inward and store it into the trash storage. The trash storage will be secured by a securing rod that you can remove it, and the storage will be free to move around. You put it back in, you secure it with the securing rod. We're planning on having the outer shell to be transparent and removable for ease of access to the components and repair.
The laser motion sensor is a selected sensor chosen by the team to detect when an object is dropped by birds into the trash analysis chamber. This motion sensor is designed as a laser grid tripwire of sorts, where the photodiode will constantly be receiving a signal from the laser. When an object breaks the laser plane, the photodiode will drop in voltage. This sends a signal to the PCB to turn on the trash imaging system and take a picture of the fallen object. A photodiode was selected in this design because of its quick rise time to recognize when a break in the laser plane happens. Other options were not able to detect fast-falling objects. A proposed idea of the laser motion sensor setup can be seen here. Here we have the design of the integrated laser motion sensor system. The dark blue mount seen here will house the laser diode and direct the laser beam towards the first mirror. The laser beam will then propagate between the front and back mirror until the light reaches the photodiode. The photodiode will be placed on a gray mount. Each mount can turn 360 degrees to accommodate for the path of the laser and find the optimal angles for the laser diode and photodiode. The large hole in the middle will be where trash brought by the birds falls. The laser grid will cover the entire surface area of the hole. Moving on to our next optical design, 2 separate lens systems were needed to capture images of the birds that approach the unit and images of the trash that the birds drop into the unit. In order to properly take images, a CMOS sensor was selected to implement into our design. CMOS sensors, compared to CCD sensors, have more noise which could create errors in the data, but overall they are cheaper, faster, and less power hungry. After selecting a proper sensor, the 2 separate lens systems needed to have specific lenses for their designated purposes. The bird camera needs a wide field of view to capture the largest of birds with a range of focal lengths from 10 centimeters to 20 centimeters, depending on how and where the bird lands. This range is called the depth of field. The trash camera needs a narrow field of view with a consistent focal length of 15 centimeters. To generalize what lenses these 2 imaging systems need, the table to the right shows what lens corresponds to a specific ideal conjugate ratio. The ideal conjugate ratio is the ratio of the object's distance from the lens to the created image's distance from the same lens. For example, an object far away from the lens that needs to be focused very close to the back of the lens has a large ideal conjugate ratio and can be approximated as infinite. For both lens systems, the object's distance will be much greater than the image's distance from the chosen lens. For example, 10 to 20 centimeter object distance will correspond to a 3 millimeter image distance. Therefore, we selected a plano-convex lens as the first lens in the system. The second lens needs to capture the image formed by the first lens and form an image onto the CMOS sensor. This is a very small ideal conjugate ratio, so a biconvex lens was chosen to be used as the second lens. Both lens systems will need an infrared filter to block out infrared wavelengths that could distort the images captured onto the CMOS sensor. The proposed general lens system design can be seen here. The major differences between the two separate lens systems will be the focal length of each lens, as well as how far away from each other they are placed. As stated before, the bird camera will need a wide field of view, so a large plano-convex lens was needed to collimate the most amount of light possible into the focusing lens. The current lens has a 90-degree field of view, and the collimating lens for the trash camera has a field of view of 25 degrees. The focal lengths of the collimating and focusing lens in the bird camera allow for a large depth of field, or range, where an object is in focus, so birds do not have to land in the same spot for a clear image.
Looking on the processing side of things, we need to make sure that our microcontroller has low power modes so that it can read sensors and not draw too much current. It needs to have enough GPIO pins in order to read from all of our sensors as well as communicate with our Jetson Nano. We need to also be able to wake this processor up from its low power mode with interrupts. It needs to be cheap, and it needs to have some development board tied with it so that it's easy to test and debug. Now, the most important are those last two, is making sure that it's cheap and that we have the development board, because almost every microcontroller fits those other few requirements that we need. And like I just mentioned, one of the biggest deciding factors was going to be looking to minimize our cost. We already own some development boards, so that made it easier to select. One of our goals was to try to stick within the Arduino IDE rather than trying to program in C, just so that we could spend more time working on the machine learning aspects of it rather than trying to sit there and debug C code, since Arduino has a lot of nice features and built-in libraries already with it. That is why our final choice, we went with the Arduino Uno that has everything we need, enough pins, and we already own it, so there's no extra purchase for a development board. Because of our selection of the Arduino Uno, we decided to stay in the same microcontroller family. This is why we're looking at comparing different Atmegas. The Atmega we went with was the Atmega 328PB because it had more than enough GPIO pins to support all of our different sensors and communication at the lowest price. We weren't too worried about any of the extra features like the ADC channels and the PWM channels, because we weren't really too worried about the resolution of how much we're seeing, because even if we do use any ADC channels, it's only going to be a very small number, not anything very wide.
Our system will utilize two custom PCB boards, a standalone power supply, and a main PCB board that controls the peripheral devices. The power supply will take 9 volts DC from a wall adapter and step it down to 5 volts to power both the Jetson and the main PCB board. A notable feature on both boards is the use of jumper pins to isolate certain sections of the circuit. This is for testing and debugging. Another feature on the main PCB board is that the stepper driver and stepper motor power are isolated from the rest of the board, so we can run it at higher voltages than the board runs on, and it just adds flexibility if we need to. We are programming the main PCB using ICSP, which has turned out to be much simpler than we thought. You just need a USB programmer. These are the Jetson communication pins. We're using the laser pins and the photodiode and the capacitor sensor. These through holes will be soldered in because those sensors will be far away from the board. Then we will have 2 servo motor headers and the trash sorter servo motor headers. We also have the power LED. We have a 5-volt break that acts as a switch, and we have leftover pins that we did not use, but just in case we need them, they're there.
Now we're getting on to the machine learning hardware options, and these are going to be really important because machine learning requires a lot of resources in order to run efficiently, and we need machine learning devices that are capable of performing object detection within 1 second of being given the data. We need enough GPIO pins to communicate with our processor on our custom PCB. And we need to be able to run 2 different machine learning models at any given time, one for birds and one for detecting cigarette butts. So the ones we're looking at here are the Jetson Nano, the Coral Dev Board, and the Raspberry Pi 4 with the Coral Accelerator. Now, all of these devices are great in their own right, but really the key things we're looking for is that we need a device that can work well on a number of different architectures. That way we're not limited by our hardware to which framework we decide to go with for our neural network. We need a device that can respond quick enough to meet our 1 second processing goal. So like I said earlier, machine learning requires a lot of resources. So we need to make sure that we have either some TPU or graphics card that can do that computation. We wanted a device that we could receive very quickly in the mail and it wasn't on back order. That way we could start working on machine learning as fast as possible. And again, we need a device that can run 2 different machine learning models, one for the bird and one for detecting the cigarette filters. Now, putting all that together, we decided to go with the Jetson Nano. The main reason for this is because of how versatile the Jetson Nano is. It can run any network and it's not limited to specifically TensorFlow, kind of like the Coral Dev Board and the Coral Accelerator are, because those TPUs are specifically designed for those. The setup for it was very easy with tutorials online on how to set up the Jetson Nano, the tutorial on how to download the Jetpack SDK, and after we set this up, the Jetpack SDK actually already had an object detection model on it as an example. And inside of those objects that it could detect, it could already detect birds, which made running this software much, much easier. So we didn't have to train our own model for the birds, and we just had to worry about training the model for the cigarette filters. Another big plus is that it came just within a few days of purchase, meaning we could tinker around with it as soon as possible to make sure that it could work with what we needed it to. After having our hardware selected, now we move on to the software side of things. Our software is pretty straightforward at a high level. So to start off, we first detect if there was a bird landing on our pad with a capacitive sensor that is being constantly monitored by the microcontroller. If their capacitive sensor was triggered, then the microcontroller sends a signal to our Jetson Nano, which then turns on the bird camera to see is the object in front of it a bird or is it something else. If it is a bird, then we send a signal back to the microcontroller saying to open the door to allow access for the bird. And then we use a laser brake sensor, which is constantly being monitored by the microcontroller again, to detect if there was a break. If there was a break, then we send the signal back to the Jetson Nano to see what the object is. Is the object a cigarette or is it anything else? So if it is a cigarette, then we sort it to the trash and we drop food as a reward by spinning a motor using the microcontroller. So earlier I mentioned that machine learning takes a lot of resources in order to run, but training a machine learning model takes even more resources in order to run, and it just wouldn't be feasible to train a machine learning model on the Jetson. So this is when we knew we had to turn to a cloud-based system in order to train our custom model. So this is when we found Edge Impulse. Edge Impulse was super easy to use. All we had to do was upload our data set on there, draw the bounding boxes by hand, and then we could run it all through the cloud-based system. One of the biggest factors for picking Edge Impulse was its ability to actually export the model into the Jetpack SDK that we talked about earlier for the Jetson Nano. So that means it was directly compatible between the two. And as you see here, we have a picture of it actually working. We were detecting the cigarette right there, even though there was a stick that could roughly be the size of a cigarette. That sometimes can fool the network, but in this case, we got only the cigarette, which is exactly what we wanted.
Here we have an outline of the budgeted expenses for the project. The Jetson Nano and the materials used for housing make up the majority of our expenses, which makes sense with image processing and weatherproofing being some very important aspects of our project. Items like the CMOS sensor and photodiode help to minimize some costs, and overall we're sitting at right under $800, which isn't bad considering the plans for replication that we have in mind. In terms of who is doing what, first Aiden has done design for both the lens system of the trash camera and the laser motion sensor, as well as housing and structural design. Next, I have done design for the lens system of the bird camera, as well as helping with the laser motion sensor and the structural design of our system. Next, Rodrigo has taken care of the PCB design, including wiring and soldering, and has contributed much to the housing and mechanical design of the birds. And last but certainly not least, Donovan has been our machine learning man, working with the Jetson and integrating our software with our hardware, as well as maintaining our website. To give a better idea of where our project currently stands, we've provided this progress timeline. Currently, both our PCB and image recognition for birds and for trash are done and ready. In the next 1 to 2 weeks, we should be finished with the laser motion sensor, which is currently being tested, and we should be wrapping up the housing and structural design, which is currently being built. In the next 3 to 4 weeks, once the structure is finalized, our lens systems should be tested and finished. And then for some future milestones, this timeline puts us on track to have a working system before the midterm demo and about a month before the showcase, as we hope to have a month for some field testing. Our hope for the project is that others will build upon our design and use it to train birds in a specific area, which could include expanding the system's capability to receiving other items of trash. The idea is that way down the road, we could see our system used in cities and on campuses to slowly minimize the impacts of littering. Thank you for taking the time to watch our design review of the bird-initiated rubbish disposal system. We're excited to answer any questions you may have.